Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit number 11, Lesson number 5, Optimizing, Day 3. So this is going to be our last lesson on optimizing, and we're going to do just a single problem. That's absolutely it. There's lots of other classic optimizing problems that we haven't tackled, many of which my students are going to be working on in groups and packets, and we're going to be going through them in class. But ultimately, we hope that this series of videos has given you a sense for how to do some of the classics in optimization. So let's take a look at the one that we're going to do today. It's really kind of neat. It asks, how close does the parabola y equals x squared come to the point 0, 1? Now what's cool about this problem is that it can kind of be generalized to the generic problem of how close does any random curve come to any random point. So we're just looking at this one in general. And you can kind of get a feeling for it, right? There's some points way out here on the curve that are, if you will, farther away, right, as measured by that distance. And then there are some points on the curve that are closer. For instance, that point, right? Now, you might think that you already kind of have the answer. You might say, well, I get it. That's probably the closest point right there, if I just measure this distance. All right. But is it, right? And the question is, how do we find that closest distance? Well, the calculus is actually pretty easy to understand, right? We take some point, let's call it x comma y, and of course we have the point 0, 1. Now, what you've probably learned before in various courses is what's known as the distance formula. The distance formula will always tell us the distance between two coordinate points. It's classically written as x2 minus x1 squared plus y2 minus y1 squared. My students know that this is just the Pythagorean theorem, right? Now, what we can do is we can say, well, all right, let's find the distance from the point 0, 1 to the point x comma y, right? And in that case, the distance will be the square root of what? I guess it would be x minus 0 squared plus y minus 1 squared. Now there's the function we need to optimize, right? We want to make that as small as possible. We want to find d min, so to speak. As usual, we've got too many variables. We've got an x and a y. So we have to think about how to get rid of one of them. Think about that for a minute. All right, hopefully you figured it out. The constraint equation here is actually pretty easy, right? Here it is. That is the constraint. We don't really have the point x comma y. We really have the point x comma x squared. That's really the point we have. So the distance is, if you will, let me deal with that. That's just x squared plus x squared minus 1 quantity squared. Now again, we could take the derivative right now, set it equal to 0, do some calculus magic, but it always kind of pays to do a little algebra. As we said in our last lesson, algebraic magic. So let's make some algebraic magic happen here. If we kind of foiled that all the way out, here's what it would look like. X squared, it's just that first one, plus x to the 4th minus 2x squared plus 1. Let's combine some like terms, and let's get x to the 4th minus x squared plus 1. So that gives me the distance from the point 0, 1 to the point x comma x squared for any value of x. Whew, I think we're ready. All right, we can find dd, that sounded weird, dx. What I'd like you to do is take a minute, find the derivative of that function. Shouldn't be too hard, does involve a little bit of messy chain rule, but besides that, it's okay. So why don't you go ahead and find that. All right, let's go through it. My students know that the derivative of the square root of a function will be 1 divided by 2 times the square root of that function, x to the 4th minus x squared plus 1. Then I have to multiply it by the derivative of the inner function. That'll be 4x cubed minus 2x. If it's convenient, if you see it, if you don't see it, you can cancel all of that. Let me write it like this, 2x cubed minus x, all divided by the square root of x to the fourth minus x squared plus 1. All right, there's our derivative. And we need to set this equal to 0 and solve. I'd like you to solve that equation, and then we'll revisit the problem. All right, let's go through it. When we have a fraction equal to 0, the only way that's equal to 0 is if the numerator is equal to 0. Be careful here. I think I'll factor an x out of both of those. That'll give me 2x squared minus 1 equals 0. A little zero product law. That will give me x equals 0, right? And if I set this equal to 0, it will give me x equals plus or minus the square root of 1/2. Think about that for a minute. If your teacher is insistent, and I am not, on rationalizing the denominator, it would be plus or minus root 2 over 2. My students are welcome to leave it as plus or minus the square root of 1/2. Whole. We've now got three critical values. So how to decide how to decide? I actually think an endpoint analysis does not work well here because it goes from negative infinity to positive infinity. I think what does actually give us some insight is a first derivative number line test. So first derivative number line. It certainly can't hurt, right? Let's take a look at it. All right, well, maybe we'll label this as d prime of x. Maybe put on negative square root of 1/2, 0, positive square root of 1/2. Of course, what we would now be doing is testing values in the derivative. One thing to note is that the denominator of the derivative is always a positive number, so all you're really doing is thinking about the numerator. And that's easy enough to do. We can test signs. We've done that lots in this course. This is the way they pan out, so it looks something like this. So what we can actually see is that not only is x equals 0, that's this point, not only is that thing not the minimum, it's actually a relative maximum, right? In fact, these two locations are our minimums, and due to the symmetry, the even nature of the original function, right? You remember studying even and odd functions? Because that function is even, these two give us the same output. They are both locations. Both of them locations of our minimum. All right. In fact, those happen somewhere, maybe we'll call this one, right? Root 1/2, comma, right? 1/2. Easy enough because y is just x squared. So that's the point that comes closest. Now, how close does it come? Well, for that, we actually have to continue to calculate. We need d min, right? Here's my distance formula. I just need to stick in the square root of 1/2 into that. That's a little bit ugly, but it could be worse. If I raise root 1/2 to the fourth, I get 1/4. Nice. Minus 1/2 plus 1. And that's going to be the square root of 3/4. And that is the closest it comes. By the way, that's approximately, had to look at that a little bit, I'm not sure why, 0.866. So that's the closest we ever come to the curve. And that's it. That's the one problem we're doing today. So I'm going to clear this out. Please write down anything you need to. All right. Well, that was a lot of optimizing problems. Not in this single video, but overall. We're going to finish off with some optimizing packets that we're going to work on, lots and lots of problems. Again, it's all about setting up the model, making sure you know what you're optimizing, creating a model that properly models whatever you're trying to optimize, eliminating any variables using constraint equations that we don't need / don't want, taking the derivative, setting it equal to 0, solving, and then using one of 3 different types of justifications to finish the problem off. All right, little summary there. For now, though, let me stop by reminding you that this has been another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.